alumni, and fellow ARES members. It's incredible to see such a strong turnout. Tonight is a celebration of the remarkable work produced by the talented engineers of ARES, and we couldn't be more grateful to have you all here to share in it. Before we begin, I'd like to acknowledge the traditional owners of the unceded land on which we work, learn, and gather today, the Wurundjeri, Woiwurrung, and Bunurong peoples. We pay our respects to elders past, present, and emerging, and recognize the enduring significance of Indigenous knowledge in academia and beyond. Throughout the evening, each sub-team will share their work, their challenges, and their breakthroughs. We'll begin with a talk from the Dean of the Faculty of Engineering and Information Technology, followed by David Parker, our Head of Business. Grace Yang, our Lead Systems Engineer, will then talk about the International Rocket Engineering Competition, IREC, which we'll be competing at this year. After that, Lachlan Whitehead, our Chief Engineer, will provide a high-level overview of our rocket, followed by each sub-team lead presenting their team's contributions over the project cycle. To round out the night, we'll be joined by guest speakers from RoboGals and Vesky, who will share their work in empowering women in STEM. But for now, you'll have to put up with me. ARES was founded in 2019. However, due to the COVID-19 pandemic, the team wasn't able to physically build rockets until 2022. That year, we constructed our first ever student-built rocket, Big Blue, alongside Phobos, our entrant to the 10,000-foot category of the 2022 Spaceport America Cup. For those unfamiliar, these height categories refer to a target apogee, or the maximal altitude a rocket must achieve without overshooting or undershooting. In our first showing, ARES placed in the top 25% of teams and was awarded the Charles Holt Award for modeling and simulation. The following year, we aimed higher, literally and figuratively, leading to the development of Deimos, our 30,000-foot category entrant. Unfortunately, a motor anomaly caused critical stresses on the rocket, rendering it unrecoverable. In response, we made a deliberate shift from solely pursuing peak performance to focusing on improving team cohesion and refining our engineering fundamentals. This shift culminated in Florence, our 2024 project. After 2 full-scale test flights, Florence achieved an apogee of 29,782 feet at competition, less than 1% shy of our target. We placed first overall in design and build quality and third in the SDL Payload Challenge. This performance earned us second place in our category and fourth place overall out of over 150 universities worldwide. Today, ARES is made up of over 100 dedicated engineers who are passionate about pushing the boundaries of what's possible. We believe our team reflects some of the brightest and most driven minds at the university. This year alone, we had over 170 applicants eager to join, further proving ARES' exceptional and growing reputation as a launchpad for engineering talent. Our mission goes far beyond just building rockets, though. We exist to give students hands-on experience, to turn theory into real-world impact, and to shape engineers who thrive under pressure, adapt quickly, and build with intent. Each challenge we face this year has helped us grow, not just technically, but as a team. We're proud to have created an environment that supports this growth, and we remain deeply committed to maintaining a safe and inclusive space for all, especially for women and underrepresented groups in STEM fields. ARES also extends its impact well beyond the competition rocket. We run an L1 certification program, organize women in STEM events, and lead outreach efforts, including bottle rocket workshops for school children and involvement in Kuori Aspirations Day. Tonight, we're proud to unveil Lemaire, our entry to the 2025 International Rocket Engineering Competition's 30,000-foot commercial off-the-shelf motor category. Named in honor of Diane Adrienne Lemaire, a fluid dynamics expert and the first woman to graduate in engineering from the University of Melbourne, this rocket represents a major step forward in our technical capabilities. I'll leave the engineering breakdown to Lockie, but I will say this. Lemaire is the product of countless hours of hard work, creativity, and resilience. could not be prouder of what we've built together. Alongside Project Lemaire, our propulsion subteam has been hard at work developing a hybrid propulsion system. Though still in its early stages, the quality and pace of work already achieved is nothing short of exceptional. You'll hear more about this exciting project later from our propulsion leads. None of this happens without the people in this room. Faculty who offered guidance, sponsors who believed in us, alumni who paved the way, friends and family who put up with long nights, stress, and rocket parts all over the house, and most importantly, the team. Every single member who gave their time, talent, and passion to make this year what it was. So from the bottom of my heart, thank you. As team lead, I've had the privilege of watching people grow, not just as engineers, but as leaders, teammates, and friends. We've seen late nights turn into breakthroughs, and impossible goals become milestones we now carry with pride. Most of all, we've learned what it means to be a part of something bigger than ourselves. A team bound by ambition, resilience, and a shared dream. So thank you. I'd now like to introduce the Dean of the Faculty of Engineering and Information Technology, Professor Das Nirmala Das.
Good evening to everyone, and really welcome to the Aerospace and Rocket Engineering Society's showcase night. First of all, please join me in giving a round of applause for all the people who's nicely seated in the front, excited to share what their kind of ambitious journey so far. Please. As we kind of standing here to kind of celebrate the outstanding work of the society, I think it is also, we should take a moment to reflect on the kind of importance of a lot of people that actually makes a difference to this type of society. You know, we have here industry sponsors, friends and family of our students, but also our industry experts and professionals who have been coaching our club throughout the journey of the society. So without their kind of support, I think it's very difficult for us to achieve the ambitions and the dream our students do have. Again, another round of applause for our people who are. As we kind of today reflect on the achievement of the society, the society really showcasing the rocket they're about to take to participating in the international competition. But I think the team mix, and then you will soon hear from them, but you will see what is on the display here. I think it is the importance of the diversity of our team here. And I think on this night, I wanted to draw on that importance of diversity as we kind of try to do the things like our society is trying to do here, how that is important to shape the innovation and kind of leadership and excellence. And I think ARES, every year, it's been really impressive to come along and see their success, and then later after the competition, join in their kind of social media post about the excitement. While we are here, we actually join the excitement, what they're going through. So again, I think we're looking forward to the next few weeks. But as a society, I think what I really like is the way that they've been able to bring together 100+ members into something really very focused and really achieving at an international scale. And then to see how they actually promote the diversity, and particularly how many women are really playing a leadership role in shaping and influencing the outcome of the society's activity. And on that note, I think there is a important legacy that we need to attribute and celebrate in them naming the project as Lemaire. And I think you briefly mentioned earlier what it is. But the Lemaire stands for a pioneer, a woman pioneer in Victoria, well known, to really shape the Victorian heart of manufacturing and innovation at the time, Fisherman's Bend, in creating an aeronautical lab and really leading major innovations in Australia. And I think that's a big celebration in you picking the name Lemaire as the rocket's name. And I think that itself is really celebrates diversity tonight. And I think the diversity is sometimes taken as, ticking off a checklist, or really, in the current context internationally, diversity has been devalued and pushed down the priority. But as we look forward to future engineering challenges and needs, we need a diverse workforce. We need a workforce that represents the population, and that's number one, is our women need to be invited and celebrated and to join the engineering profession. So society like this is playing a big role in that context. And it is not just about women, but it is, you will see, the diversity actually cuts across a number of different ways within the society's team. So at the Faculty of Engineering and IT, we remain committed to this mission of embracing diversity in every way possible. But through scholarships, mentoring programs, outreach initiatives, and industry partnership, we work to support and encourage more women and non-binary people to pursue, thrive, and lead in STEM fields. It's not only about increasing numbers, as I mentioned earlier. It's about visibility, it's about representation. It is about ensuring that next generation can see themselves embedded in every facet of engineering. Our aim is to cultivate a culture of genuine inclusion where diverse contributions are recognized and valued. So the projects like Lemaire, the ARES has shown what's possible when different perspectives and collaborative leadership can come together. Every member contributes their unique skills and insights. Together they achieve what no one could alone achieve. It's a testament to how embracing a diverse voices through a shared vision can drive technical excellence. As I mentioned, this project is actually honoring Diane Lemaire, and her kind of legacy is living with us through a particular scholarship program supported by a trust that she helped us to establish. So the bequest from Diane Lemaire actually supports female PhD students in our faculty, and through this program, Legacy of Diane continues to inspire women pursuing aerospace engineering and STEM-related careers. And I think, so it's again a reminder what is possible when barriers are broken and new opportunities are created. Let me finally congratulate the ARES team. Your dedication, technical expertise, and countless hours of work, often outside your classes and jobs, have culminated in an outstanding project. And student teams like ARES play a pivotal role in shaping future of engineering and technology. Projects like Lemaire encourage our students to delve deeper into comprehensive solutions. It allows them to explore all sorts of solutions around a global challenge. And they also learn to how embrace the diversity and how they can collaborate effectively to address that global challenge. So as you prepare to kind of represent our university on the world stage at the International Rocket Engineering Competition this June in Texas, we wish you every success. While we are here, we are with you in Seoul and Sprit, and we will be thinking of you as you put your final touches on your rocket, and we will be closely following the launch trajectory from far. So you carry the pride and the support of our faculty and the university, and everyone gathered here, because they've been turning up to really give you moral support as you embark on this journey. So we wish you the very best in the competition, and thank everyone for attending and supporting our society's efforts. Thank you.
Thank you, Professor Faz, for your kind and inspiring words. My name is David, and I've had the privilege of serving as the head of The head of business is primarily responsible for managing our budget and overseeing procurement. Throughout the year, we've faced some significant and unexpected challenges, many outside of our control. But despite these challenges, the team has found ways to adapt, deliver, and ultimately thrive. This isn't due to some hidden magic on the part of the leadership team, but rather it's thanks to the remarkable skill, passion, and perseverance of our members, and the incredible support we receive from our university, industry partners, and personal networks. I'd like to take a moment to thank some of those people. First and foremost, our academic and teaching staff. Thank you to Richard Sandberg, our academic advisor, along with Andrew Uy, Yi Yang, George Chen, Steve Adams, Chris Honig, Carol Barry, and Joe Staines. Your guidance and belief in our work has been instrumental in getting us to this point. We're also immensely grateful to the FEET professional staff, particularly those in HSW, student wellbeing, and student engagement, for your advice, encouragement, and for helping us foster a team culture built on respect, safety, and growth. To the infrastructure services team, our facilitators, Michelle McKay, Steve Beard, and their team, countless times during this cycle, they've helped us solve our problems, presented us with opportunities, and helped us find a path to achieve our goals. Beyond the university, the creator space has been vital. Paul, Alex, Nessa, Travis, Max, and Jane, and their team of incredible student guides, many of whom are ARES members, I might add, have been generous with their time, expertise, and equipment, facilitating not only the manufacture of our rocket, but many of our outreach programs. To our long-standing industry partners, Machine for our precision components, GLH for continued support with our recovery systems, Anton at Auto Vanity, whose incredible paintwork is behind the stunning finish on Lemaire. I'm sure you'll all agree that we will continue our proud tradition of having the most striking rockets on the field. To David Boyd and the Victorian Rocketry Association, your vital support, launch site, and your rocketry expertise continue to enable not just us, but teams from across Victoria and beyond. And a special thanks to Accor, Epsilon 3, LEAP, OnShape, Pelican, CW Laser, Boeing Australia for their ongoing support, and Jack Beavers for again facilitating testing at the Tyabb airfield. This cycle, we've also been fortunate to grow our support network. Firstly with Blackmagic Design, an Australian company producing world-leading camera and production technology, who has helped make tonight's live stream possible. We're excited to continue working with them and sharing our journey far and wide. Our other new partners include Compliance Engineering, NewTek, Pacific Automation, LabJack, 8020, BOC, Synex Labs, Wiedmuller, HP, Parker, and Ritar, who have allowed our propulsion dreams to finally begin becoming a reality. And finally, to the team, to each other. ARES is much more than a student project. It is a community. I have witnessed and personally felt support, encouragement, and the inspiring drive that each of you bring. This team is something special, not just because of some pretty rocket, but because of the people. You've grown into phenomenal engineers, scientists, and humans. And you should be all so proud of yourselves and this team that you represent. Thank you for letting me be a small part of it. I'll now hand over to Grace to walk us through the details of the competition.
Thank you, David. Good evening, everyone. My name is Grace, and I have the privilege to serve as the system engineer of ARES for this project cycle. So this year, the International Rocket Engineering Competition, which also known as IREC, will be held at Spaceport Midland in Texas. It's the world's largest student rocket competition, bringing together over 150 universities from across the globe. Teams will compete in 8 different categories, ranging from student research and design solid and hybrid motors to multi-stage rocket reaching up to 45,000 feet, as well as COTS, which, as mentioned before, commercial off-the-shelf rocket at both 10,000 feet and 30,000 feet. So our team will be competing in the COTS 30K category. What that means is that we are using a commercially available motor rather than building our own propulsion from scratch. But we're also working on our very own hybrid motor, which I'm sure you will hear more about tonight. And with a development, we're hoping to bring it to competition in the very near future. So the goal for our rocket this cycle, Lemaire, is to fly exactly to 30,000 feet. Not a foot higher or lower. And to help us achieve this level of precision, we designed Lemaire to slightly overshoot and included an active air brakes control system, allowing us to fine-tune her apogee mid-flight. And with this system, we are confident that she will hit the target. At IRAC, we will be judged on more than just the flight performance. Points are awarded for design and build quality, as well as a successful recovery of the rocket. We have already also submitted 3 progress reports and a very comprehensive technical report detailing every aspect of Lemaire's design. And beyond the core competition, IRAC also features several optional challenges, including the SDL Payload Challenge, a team video challenge, a simulation challenge, and some other technical awards which are only given to those granted podium session. And good news is we got the podium session last night, so let's go. Yeah, so we're incredibly proud to present what we've achieved this year and even more excited for what's ahead. And thank you all for being here tonight to share this journey with us. And I would now like to welcome Lachlan Whitehead, our Chief Engineer, to introduce Project Lemaire.
Hi everyone, my name's Lockie. I've had the pleasure of serving as Chief Engineer of ARES for the 2025 project cycle. Tonight I'll just be giving a brief overview of our rocket Lemaire. So, the 3.1 meter tall rocket will accelerate to a maximum acceleration of 22 Gs, reach a top speed of 1.7 times the speed of sound, and coast to a target of 30,000 feet above ground level. It's powered by a commercial O5500 solid motor, which fills the entire lower half of the rocket and has an average thrust of 5.5 kilonewtons. To hold together the rocket under that immense stress is the rocket's composite airframe, comprised of carbon fiber body tubes and fins, and a fiberglass nose cone and boat tail. Starting from the top of the rocket, we have the Avionics bay, which houses our commercial electronics as well as our student-developed ones. These tell us where the rocket is, how fast it's going, as well as controlling our air brakes and our parachute system. Speaking of which, below the Avionics bay, just above the bolts you can see in the middle there, is the recovery bay. This houses both our parachutes as well as their deployment systems. Lemaire follows a single separation dual deploy recovery scheme, which you'll hear about from our recovery lead Ben later on. Below that, we have our payload. Lemaire's 145.2mm diameter is the smallest possible that can fit our 3D CubeSat payload. The payload tests the robotic arm's accuracy in performing high precision movements in extreme acceleration and vibration environments, which the rocket provides. Below the payload, in that silver area there, is the integrated coupler. It features a video camera to film the ascent of the rocket, as well as our air brakes, as Grace and Patrick have talked about, which will slow our rocket down to an exact apogee or maximum altitude of 30,000 feet. Lemaire is an iteration of what was a novel design for ARES last year, the successes of which have inspired many design decisions of this year's rocket, but just as much have the failures. ARES' goal with Lemaire was to refine this architecture into a repeatably successful competition entry, and I'm proud to say that ARES has done everything we can to make that a reality. You'll hear from our sub-team leads next about just how optimized this beast is. But before that, I'd like to express just how proud I am of the entire team and their work, which I can confidently say will blow the judges away in the States, and how grateful I am for being given the opportunity to help lead such a brilliant team. Speaking of brilliance, I'd like to invite Lachlan Meagle and Simon Lee up to show you the work of the structures sub-team.
Good evening, everyone. I'm Simon. I'm one of the structures leads alongside Lachlan for this project cycle, Lemaire. The structures team is at the core of the design and manufacturing of Lemaire. From the internal bulkheads to the outside fins, we are responsible for the final geometry and strength. As such, we also work very tightly with the other sub-teams, such as Avionics and Recovery, to ensure ensure their systems integrate seamlessly into the airframe and can operate as designed, allowing us to perform our best at competition. Lemaire is an evolution from our previous competition rocket, Florence, featuring lighter bulkheads and larger fins for better flight stability, as well as redesigned internals for more advanced avionics and recovery systems. She also features new technologies such as our in-house retractable railguide systems and our vacuum bag tip-to-tip. Talking about the bulkhead, our bulkhead in the middle, as shown, was already busy. However, upon innovation from avionics and recovery that you'll hear about later tonight, it has gotten even busier. As such, it had to be reimagined in order to accommodate these new additions, which include over 9 different components. Part of these changes was to shift the internal U-bolts as well as the surrounding threaded rods, as well as lowering it in the nose cone for better access. Now, this redesigned system can now be integrated externally from the rocket without even having to be inserted inside. This allows for faster and safer integration, which is crucial for time crunch moments such as IREC launch days, giving us time and safety during these intense periods. Our next innovation was the Payload bulkheads, where we implemented the use of topology optimization in conjunction with finite element analysis in order to produce lighter bulkheads that allow us to fly higher. We successfully redesigned payload retention from 315 grams to 98 grams, whilst retaining a safety factor of well over 2. Not only are we reducing the overall mass of the rocket, we do not compromise on its safety. Our biggest research project this cycle was our in-house designed retractable railguides. Railguides are small round pieces that keep the rocket straight as it accelerates on the rail. Last year's railguides were rigidly fastened to the rocket body, but remained on its outer surface. As such, even though it is a small geometry, when the rockets reach speeds of almost Mach 2, these small pieces do create a lot of drag. As such, we redesigned this year's iteration to retract into the rocket instead, leaving a seamless surface for undisturbed airflow. This allowed us to comfortably hit over 30,000 feet and use our air brakes to trim the remaining height. This design took several months of prototyping and researching, and a few extra to completely manufacture. A special thanks to the staff at TCS, namely Travis, Max, and NASA, who've helped it come to life. I'm proud to say that they've been flight tested twice and have performed as intended. Although simple, these guides show our growth as a team and our ability to design and manufacture in-house projects. All our projects could not have been possible without the endless talent of our structures members, who, alongside their full-time coursework, spend countless hours putting in work to create the rocket before us. Now, I could talk about the design of the rocket all day, but the manufacturing of this beauty is just as exciting. So I'll pass the mic on to Lachlan, who will talk about the intricacies of manufacturing this rocket from scratch.
Thank you, Simon. Good evening, everyone. My name is Lachlan, and I'm the other structures lead for Project Lemaire. Watching Lemaire go from a CAD file to reality has been an incredibly rewarding experience and could not have been done without the hard work of every structures member. Our manufacturing period began in earnest, where we focused on preparing jigs, creating molds, and producing parts in the aim to upskill members in the land of composite manufacturing. One step forward we took in our manufacturing is vacuum bagging our tip-to-tip. A tip-to-tip is a process that involves laying a few layers of composite cloth, such as carbon fibre, from one edge of a fin to another, improving fin strength and rigidity. To vacuum bag this process involves laying the cloth that has been wetted using resin, and then utilising a bag large enough to cover the fin can and pulling a vacuum. The benefits of this include a more even distribution of resin, reduction in air bubbles, and a compression of the cloth. We tested this on a subscale rocket before implementing it into our test rocket and eventually onto Lemaire. The results of this have invited further innovation, with current development into a resin-infused fin can, where a few members have been developing subscale prototypes of the fins and body tube as one piece, what I hope to soon become standard practice for ARES in the future. Now, moving to the top of our rocket. Nose cones are typically a difficult part to produce due to their tapering nature and need for a smooth external and internal finish. We decided to reuse the molds from the previous cycle, attempting to create a repeatable process. The first few nose cones weren't without their issues. We were doing the same thing over and over again and expecting different results. However, after some final tweaks to our process, our team was able to produce the beautiful nose cone you see here atop Lemaire. The nose cone we built has that incredible outer surface for aerodynamic performance, as well as the beautiful inner surface you need for mounting the bulkhead. Moving forward, we hope to shift from using wooden moulds in this nose cone to a more robust fiberglass mould to provide more repeatability in our process and longevity in the moulds. One of our more recent projects has been creating the resin-infused fiberglass recovery compartment. The benefit of a fiberglass recovery compartment is to increase strength and ensure our main parachute is better protected during separation. This project kicks off what will be the first of many resin-infused parts and adds a new dimension to our composite manufacturing capacity. Finally, Simon and I would like to express our deepest gratitude to every Structures member. It has been an honour to lead and work with you all. Every single member has brought passion and dedication to the team, as well as their own unique strengths. It has been a privilege to watch everyone become incredibly talented designers and manufacturers. Over the last 12 months, there have not always been a straightforward path, yet here we sit admiring the fruits of our labour. We believe all of you are destined to become wonderful engineers and can confidently say the future of structures is in safe hands. I'll now pass over to Anindo to talk about aerodynamics and simulations. Thank you.
Hi everyone, I'm Anindo. I'm the Aerodynamics and Simulation Subteam Lead for Project Lemaire. First off, I would like to thank everyone in ARES. Without you all, that we achieved this project cycle would have been impossible. So what do? AeroSims, we are responsible for the optimization of the rocket shape, generating drag curves, flight simulations, and in conjunction with Avionics, working on the logic of the air brakes. On the aerodynamic side, our primary goal this project cycle was design optimization, building on last year's success in Florence. We did this by refining the nose cone, bow tail, fin angle, and chamfer. Each of these studies was preferenced with a mesh independent study, which analysed the optimal mesh for our computations. A finer mesh means finer detail and more accuracy, but it also takes longer to compute. We then analysed which shapes perform best at subsonic and supersonic speeds, considering both aerodynamic efficiency and manufacturing constraints. For example, our new bow tail design generates less drag at supersonic speeds than Florence's, which is crucial. As you can see by the graph above, this approach, as well as Structures' innovative and incredibly cool retractable rail grades, means that we were able to decrease our supersonic drag by roughly 25% compared to Florence. However, as we near competition, our responsibility shifted to generating as accurate drag curves as possible to inform our simulations on the day. So we use CFD at different Mach numbers and airbrake extensions to create a detailed drag profile, which then directly feeds into our flight simulations and improves their accuracy. On the simulation side, we also use a variety of simulation tools, including RAS Aero, RocketPy, and OpenRocket, alongside an arsenal of in-house tooling. We've enhanced our simulations by improving our weather modelling capabilities and refining our Monte Carlo techniques. Monte Carlo simulations enable random sampling of rocket environmental and flight parameters within expected ranges. By running millions of simulations, we can identify conditions that are unsuitable for launch and determine when the rocket is likely to converge to a 30,000-foot apogee. However, our main project this cycle has been the air brake system, designed to help us hit precisely 30,000 feet of competition. How does this work? We pre-compute flight data into a multi-dimensional lookup table covering all realistic flight scenarios. Since this table is too large for onboard storage, we compress it using a neural network which maps the data efficiently and governs the apogee in real time. This is a section in the control logic which is then used within the wider flow to determine the extension. To validate this, we developed hardware-in-the-loop testing, allowing us to simulate and test airbrake responses using both pre-computed flight data and past flight data, which is essential given the challenges of live testing. In summary, by combining accurate drag data, robust simulations, and advanced machine learning, we're making Lemaire our most optimized and reliable rocket to date. Thank you again to my amazing sub-team for your dedication and expertise.
Avionics plays a crucial role in tracking the rocket, providing accurate data for flight analysis, and triggering recovery events at the correct time. Our team is composed of a wide range of diverse students from across electrical, mechatronics, and computer science backgrounds, who will work to develop custom electrical hardware, write necessary software, and carry out launch day operations. This project cycle was able to build on the strong foundations of the previous year's systems. However, we also identified key areas for refinement. Most significant was the addition of the communication bus through the whole rocket, allowing seamless data sharing among the whole avionics systems. The system comprises the avionics bay sitting in the nose cone of Lemaire, the air brakes bay inside an integrated coupler, and the ground station, which allows communication with the rocket. To make use of the new communication bus, a focus was placed on developing custom hardware, namely an air brakes controller, a power distribution module, and a wireless communications gateway, as you can see highlighted here. Abstracting from the hardware to the software world, behind me you can see a high-level view of the avionics systems. Data originates from our primary flight computer, Hermes, located in the top right. Hermes performs flight logic and reports the rocket's current state. It contains many sensors that combine using a state estimation algorithm, specifically a Kalman filter, that extrapolates data from the available sensor information to predict parameters we cannot directly measure, such as velocity, while increasing our confidence in other measurable values. This data subsequently travels through the rocket gateway, which clusters information into large packets for transmission to our ground station. Importantly, this information is also communicated to the air brake system, enabling execution of the models previously discussed by the Aerodynamics simulations in the subteam. Finally, on the ground station, this year we have developed a single pelican case that houses all the equipment required for flight day operations. The ground station features a centralized data handler, which routes the packets received from the rocket to both a web interface and connected laptops, providing real-time access to flight information. The web interface also allows control of the rocket, letting us arm systems and start camera recordings. I couldn't be prouder of the team's hard work and achievements this project. It's been a remarkable experience working alongside such a passionate and talented group of people. I've enjoyed everyone's unique perspectives during our meetings, and the many discussions, quite often tangential to the original purpose, but it pushed me to critically analyse all my decisions, and I hope have pushed the Avionics team too. It's been an absolute privilege working with you all. I'll now pass on to Sarah to talk about the amazing work of the Operation and Logistics subteam. Thank you.
Hi everyone, I'm Sarah and I am the Operations and Logistics Lead for this project cycle. I hope everyone's been having a lovely night so far and it's so great to see such a big turnout. So what does the operations team do? We primarily take care of all the events, marketing and logistics of ARES. So this includes managing stakeholder relations, creating merchandise for the team and planning logistics for when we're in the US. This semester in particular, we coordinated and delivered several large-scale events, and this is something that I am really proud of. So for example, this March, we collaborated with the Faculty of Engineering and IT to represent the university at the Avalon Air Show. A total of 14 members attended and assisted the 6-day event, where we spent our time speaking with industry professionals, sponsors, and families. Then in April, we collaborated with several student engineering clubs to host Industry Night, where students and industry representatives came together in a professional networking setting to share insights into engineering careers and internship opportunities. Then in May, we directed our focus to tonight, Showcase Night. All the planning, marketing, catering, graphic design, events like these require months of preparation, and this was all done by the lovely operations team. I couldn't be prouder of each person's vision in bringing these nights to life, and it really is so rewarding to watch such hard work culminate in successful outcomes. Another highlight of this cycle began at the beginning of semester 2 last year, where we all came together and sat in a very long meeting to create some big picture goals or visions for the operations team. One such vision was to encourage the greater sharing of rocketry knowledge amongst ARES and the wider community. Rocketry can sometimes feel intimidating and exclusive, and even within ARES, many sub-teams are so deeply focused in their own work that they don't really get a chance to learn about the progress of other sub-teams. So, throughout the cycle, we've worked on creating Rocketry 101 videos, where we select a particular structure or technique and break it down simply in a short-form video. We also have an internal ARES newsletter that is released every Monday and now features a rocketry glossary. And as a bonus, our full team meetings now feature a segment called a Tech Talk, where members from various sub-teams develop a presentation sharing their area of work to the rest of the team. I hope we continue to foster this this culture of learning and curiosity, and I hope everyone here feels inspired to do the same tonight. And finally, to my operations members, I want you all to know what a privilege it has been to be your sub-team lead. Watching everyone become so capable and able to take on larger and larger responsibilities has made me appreciate just how far we've come over the course of a year. Your behind-the-scenes work is truly what keeps the team running. And on a personal note, the friends I've made in ARES will forever be the highlight of university. So, to my sub-team and the wider team, please just know how much I appreciate you all. Thank you, and I'll now pass it on to Diane.
Good evening, everyone. I'm Das, and I've had the privilege of leading Payload this project cycle with Lemaire. Payload at ARES has been traditionally, for the past 3 years, we've always been investigating biomedical phenomena under high AG environments. Last year we looked at bacteria sampling, but given the engineering strengths of this team, ranging from mechanical engineering all the way to electrical and computer science, Payload took on our most ambitious project ever, which is Project Lemaire. As space travel increasingly gets more and more accessible every single year, Tetra serves as a technology demonstration, a proof of concept of a mechanical system that is able to perform high-precision tasks under high acceleration and vibration. The demonstration that we produce within the rocket serves as a potential framework of the construction of surgical and manufacturing applications. Inside the rocket, our main objective this year is to sketch a straight line and numerically analyze our performance using 3 key criteria. Number 1, the line straightness that we draw. Second, gradient distribution. And number 3, our pressure consistency that is applied by the pen while actually drawing. And these 3 key criteria basically dictate the viability of the system in the applications we intend to use it for, as suggested earlier. A common theme of this year's project cycle was a high emphasis on in-house design and manufacturing in all 3 of our departments, which I'll touch on a bit later. The 3 key departments that we have, we kind of operate as our own mini areas in itself. We have our own structures team, we have our own electrical team, and we also have our own software and data procurement team. Okay, so firstly, looking at structures. Structures is responsible for modeling the Tetra, okay, so basically producing the forearm configuration that we have here, and also assemble the payload chassis to make sure that it can be easily assembled and disassembled while in competition, and it actually has a logical layout. Some of the key project structures was actually involved in was actually handcrafting the aluminium brackets on the side, as well as the motor plates that we use, where we kind of refined them and drilled them at the telescopic spaces. Thank you to them. Additionally, the team actually designed the way to operate the Tetra, featuring a forearm ball joint system that allows the centerpiece to maintain both angular and translational position, so it doesn't automatically rotate on its side. Next, we have our electronics team. Okay, so electronics is responsible for designing in-house PCBs and integrating various electrical systems in play, including the new addition of a battery management system. The electronics department's key project this cycle was the development of 2 PCBs, one for managing power and connection for all of the sensors that we use, including the pressure sensor and the accelerometer, as well as also producing another PCB to establish connection between our microcontroller, which is our Raspberry Pi, and our stepper motors, which drive the 4 actuators that produce the robot. The design of the 2 PCBs that we used allowed us to have more freedom in where certain components and systems were placed in the unit, which made this really strong for our campaign. Additionally, for the first time ever in Payload, the team incorporated a battery management system. It's a way of maximizing battery life and also maximizing the battery's efficiency and effectiveness by preventing overcharging and over-discharging throughout the actual operation of the payload, which you can see is on the right. And last of all, our software and data team. we're responsible for designing the accommodating software needing to control the tetra, as well as providing various data acquisition protocols and methods for the most efficient and effective analysis. One of the key developments of the software team is the actual tetra algorithm that drives the mechanical system. Given the lack of documentation on the system, we generally have delta arms and core XY sort of movements. We've never actually seen a tetra robotic system before. So given the lack of documentation, we had to design our own mathematical models and simulations to be designed from the ground up to help us understand and build a system where we can actually draw a straight line as well as possible. And maintain tetra's versatility in the applications it can be used for. Our other analysis system, which you can see on the right, features a custom-made applet on Streamlit, providing information on all of the key criteria which I went through earlier on that needs to be measured to assess the performance of tetra. Where we seamlessly integrated computer vision on detecting the line straightness using OpenCV, as well as using basic data structures to analyze how well we've maintained pressure and how well we've maintained our accuracy in drawing the line as much as possible. So last of all, I'm incredibly proud of the efforts of the Payload team this cycle that we've made. From being the team that generally finishes their product on the night of the competition, having a prototype for showcase night is amazing to say the least. So thank you very much. It's an incredible privilege to getting to know you all and working alongside such a talented group of individuals. I'll now pass on to Ben to talk about the amazing work that has been going on in recovery this cycle. Thank you very much.
Good evening, everyone. I'm Ben, the recovery team lead for this cycle. Our small team are focused on the most delicate and nerve-wracking part of rocketry. While everyone else focuses on the way up to 30,000 feet, the recovery team is in charge of bringing the rocket back down. We do this by separating the rocket into two parts at 30,000 feet, and then using a collection of lines and two parachutes to ensure it isn't damaged at touchdown. The separation process has redundancy, with the primary method being our student research and developed ejection charge, CO2 ejection system, while the backup being our novel ejection charge method. The parachute and line system we use is the more complex and unpredictable part of our system. It includes 18 different fabrics which are specifically chosen for their unique properties, such as the flame, my bad, here's some photos as well, wow, such as the flame resistance of Nomex and the porosity of ripstop nylon. My description so far implies that rocket recovery is a standard engineering challenge, but this isn't quite the case. The true challenge of recovery is that there's no university class, no reliable sources, no simulation software, and no default solution to almost any part of the process. This means that of the 150 plus teams that will be competing at IREC, every one of them will have a different system. Additionally, many parts of the recovery system must be manually packed and integrated in the days and hours leading up to launch. The stakes for these processes are extremely high due to the incredibly narrow margin for error. Any minor procedural error, such as how the parachutes or lines are packed, can lead to catastrophic failure. So how do we combat these challenges? Firstly is the procedural side of things. This year, countless hours have been spent repeating, refining, and precisely cataloguing the exact processes we use to bring our rocket back down. The second aspect we work on is the development side of things, where the team has waded into two ambitious projects that will hopefully fly next cycle. The first of these is developing our own parachutes. After scouring every source on round parachutes, the team started experimenting and improving manufacturing methods before recently finishing the early stages of our first prototype. The other project is a clamp band, which is a more reliable and safe method to separate our rocket. We've been designing and iterating on these components before hopefully pushing forward with manufacturing and testing early next cycle. What probably won't surprise you after my description of the job is that there's a lot of testing involved as well. So here are some of the tests we've got. We've got a big electromagnet that's pumping about 30 Gs through that sampled nose cone. In the middle we've got a few car testing photos. So that's the rig where we deploy parachutes out at the tie-up airstrip. And then on the right, there's some Instron testing, which is just a tensile test and measures the displacement across that test. So these tests, along with many others, have allowed us to uncover potential issues and validate some of our systems. We design these tests before often manufacturing parts to make them possible. We then execute the tests, analyze the performance of our components, and then use that data to alter our system. This huge job has only been possible with the incredible team I've had. What started with just Lily and I has become a team of talented, reliable, and cohesive engineers who've come to launches in staggering numbers. I also must say thank you to our secret weapon, Crass. Crass is one of the most experienced and skillful skydivers and parachute riggers in Australia, whose generosity and his knowledge, his time, his resources has always been astounding. Thank you very much. Up next is the Propulsion team to talk to you about the future.
Good evening, everyone. I'm Neil, and this is Jack, and together we have had the privilege of leading Propulsion here at ARES this project cycle. At last year's showcase night, I gave you a glimpse into what the future of propulsion at ARES might look like, and hinted that hybrid rocket engines were just around the corner. 1 year on, I'm happy to say that future has arrived. And tonight, we're excited to show you what we've been building. So just to start with, let me give some context as to why we're developing our own engine. As ARES rockets continue to grow in complexity, carry more avionics, large payloads, and more sophisticated experiments, it's becoming clear that we need a propulsion system tailored to our ambitions. Importing solid rocket motors has become increasingly difficult and expensive, but more importantly, building our own hybrid engines unlocks an unmatched educational experience. We're now delving into new engineering disciplines like fluid dynamics, thermodynamics, control systems, and test engineering, and giving our team members hands-on experience with technologies used in the cutting-edge aerospace industry.
Now you might be asking, what exactly is a hybrid rocket engine? So a hybrid rocket engine combines a solid fuel, in our case paraffin wax, with a liquid oxidizer, nitrous oxide. The oxidizer is injected into a combustion chamber where it reacts with the solid fuel, producing high temperature gases that expand through a nozzle and generate thrust. It's a best of both worlds system. It's safer than traditional solid or liquid engines, relatively simple to operate, and it can be throttled down or shut down mid-burn, which is something you can't do with a solid motor. So we spent the past 9 months or so developing our first subscale hybrid rocket engine, a crucial first step towards our full-scale system. This engine is not just a proof of concept, it's a fully integrated system with the same support architecture as our future competition engine, just with a smaller and less powerful combustion chamber. So this subscale project has involved various subsystems, and it will take you through arguably the most critical, which is the data acquisition and control system.
So this system acts as our eyes, ears, and brain of our entire setup. Its job is to constantly monitor the engine and support systems using a network of sensors measuring things like pressure, temperature, and thrust, and then use that information to safely control valves and ignition systems. We've been lucky to receive high-quality sensors and electronics from LabJack and Pacific Automation, and we've spent a lot of time carefully wiring everything together, like you see in those images there. It's a central hub that keeps the whole test operation running smoothly. And in order to communicate with the test stand, which could be up to 600 meters away, we've been using mil-spec fibre optic cables provided by Optical Solutions Australia in conjunction with 100 gigabit networking gear provided by Blackmagic. We're also excited to be working with Synax, a company that makes test and control software used by several leading aerospace companies in the US. Their tools allow us to design robust and flexible control processes for everything like characterizing engine performance, to tank filling and ignition, while also adding layers of safety. Now, Black, would you like Jack to talk about the fluid system?
So this data acquisition and control system that Neil's just explained, it pretty much exists primarily, at least, to control the flow of fluids onto and out of the rocket engine. So this fluid system itself is the physical set of valves, pipes, and components that deliver high pressure nitrous oxide to the rocket flight tanks, and also allow for secondary functions such as purging the system with nitrogen, venting tanks, and igniting the combustion chamber. So executing these tasks on time is obviously critical for safety and for keeping everything repeatable and reliable over time. And thanks to the generous support of some of our sponsors, HB Aviation and UTech, we've been able to design a solution for remotely controlling this fill and launch sequences from hundreds of meters away, which we call the GSE, or Ground Support Equipment cart. So the GSE cart combines the fluids hardware with our DAC and control cabinet into a single portable system that we can use not just for testing but also for launch operations. We've also designed it to be engine agnostic, so it doesn't just work with this subscale engine. We'll also be using the same carb with our full-scale engine and even future rocket designs later down the road. So by building reliable infrastructure that scales with us, we're able to focus on the innovation of each engine without starting from scratch with our support equipment. So now onto the engine itself. For our subscale combustion chamber design, we chose to go with pretty tried and tested methods of construction, ensuring that we prioritize reliability and robustness, especially for our first engine. So the outer casing as well as the forward and aft closures are made of aluminium, with phenolic being used to protect the aluminium from high internal temperatures. Finally, a graphite nozzle insert is used to pull heat rapidly from the throat and dump it into the phenolic. All of these parts were graciously manufactured by our long-standing partner Machined in Adelaide. They've got some incredible parts. We've got some of them have started to arrive, and we've got them on display upstairs, so definitely go and check them out. The final part of our engine is the fuel grain, and Neil's going to take us through the manufacturing of that part.
So for our hybrid engine, we utilise paraffin wax as the solid fuel due to its safety, availability and strong performance characteristics when paired with nitrous oxide. To ensure consistent performance and quality, we've adopted a spin casting process to manufacture our fuel grains. So spin casting involves pouring molten paraffin into a cylindrical mould and then spinning it while it solidifies. This rotation promotes uniform density and minimises voids, producing fuel grains with highly accurate outer diameters as well as inner diameters. The casting rig consists of a motor-driven spindle housed within a shielded enclosure, and then this spin casting enables us to fabricate consistent, scalable fuel grains efficiently while maintaining strong safety and quality standards along the way. We're currently also looking into adding additives to the paraffin to increase its structural characteristics as well as optimise regression rates, and this is something we'll be doing over the next course of the next couple weeks and months.
So on the topic of optimization, our incredible modelling and simulation team have been developing a whole suite of engine design tools that allow us to rapidly iterate on designs and compare real-world test data with our best predictions. So on the slide behind me is a screenshot of the graphical user interface for the chamber simulation tool, which is currently being used to create test matrices for our subscale testing campaign, so we can make sure we're hitting all the performance marks we want to see from the engine. So as much as we do love our tiny little subscale engine, it really is just the beginning of the ARES propulsion program. We're already transitioning towards our first full-scale engine, which will build on everything we've learned from the subscale program and aim to be capable of launching a competition rocket to 10,000 feet using fully student-developed propulsion. So we're really looking forward to transitioning into full-scale development of the flight engine next semester and using what we've learned from the subscale testing to inform our future designs.
None of this would have been possible without the tireless work of the team and the incredible support from our sponsors, mentors, and the Faculty of Engineering and IT. From the aluminium extrusions that hold our rigs together to the studio cameras and broadcast equipment that will bring our tests and launches to life, the machining services that make our engine parts reality, our sponsors have provided us with the tools, materials, and support we need to do world-class engineering. And they're not just sponsors, they're partners in education and innovation, helping us push boundaries of what students can achieve. But finally, we want to say our biggest thank you to our propulsion team, 17 of the most dedicated, curious and hardworking people we've had the pleasure of working with. You've poured hundreds of hours into this project, often late at night while juggling uni, work and life. Embarking on new projects is never easy, and what you've all accomplished is remarkable. It could not have been done without you. To our supporters, our sponsors and the ARES team, thank you, and we're just getting started. So now I'd like to introduce our guest speakers who will be spotlighting two different organisations that work towards promoting equity and inclusion in engineering. Can we please welcome Isabella and Nat to the stage? Thank you.
Good evening, everyone. My name is Bella, and today I wanted to talk to you a little bit about a program that I've been involved in, thanks to the wonderful organisation VESCI, to help empower high school girls to be interested in studying in STEM fields. So VESCI is a Victorian organisation established to enhance Victoria's intellectual capital through international networking, fellowships and awards, with a focus on developing women's careers in STEM. As a part of this, partnered with the Avionics Institute, they run an industry mentoring program each year with girls from different high schools. And earlier this year, they reached out to ARES to ask if any of our female members would be interested in being a mentor, which is how I'm lucky enough to be a part of this program. The program runs over a 6-month period where I'm given a group of students and help them develop an oral presentation in my area of study. So for this, I chose to do something that relates to what I do in ARES, how drag force changes at different Mach numbers, as I'm in the Aerodynamics and Simulation sub-team. I've been partnered with 2 girls interested in studying aerospace engineering and astrophysics, and they've been finding it really interesting to learn some new things that they haven't heard in class. I chose to be a part of this program because I wanted to share my interest and passion for what I'm studying with these girls, and I wanted to encourage them to have the confidence in themselves to achieve their goals. ARES looks forward to continuing to be a part of this program in future years, empowering young women.
Hello everyone, my name is Natalie and I'm the Vice President of RoboGals Melbourne. We are a student-led, not-for-profit organisation that aims to make STEM more inclusive and accessible. We do this through our free hands-on STEM workshops, which we run at primary and high schools all across Victoria. Over the past year alone, we've reached more than 2,000 students, with 60% of them being girls. Whether students are working with our Spike Prime Lego robots, programming and building traffic lights with Arduino and C++, or coding shapes with Python, we aim to show them that they are capable of engineering and can also have a little bit of fun with it. These workshops aren't just about learning basic technical skills though. They're about sparking curiosity, building confidence and challenging outdated ideas about who can be an engineer. Because it isn't just enough to simply invite people into these spaces, we need to make sure that they feel a sense of belonging. And at RoboGals Melbourne, we are committed to creating that sense of belonging and showing women that they do belong in engineering. So thank you so much to ARES for inviting us to speak tonight and for creating such a wonderful space to celebrate women in engineering.
Thank you so much, Bella and Nat. As we near the end of the presentation, I wanted to say a few words of gratitude on behalf of ARES. So firstly, I'd like to thank the operations and logistics team again for bringing tonight to life. It really takes such a talented group of people to make such a big event possible. So can we please give them a massive round of applause for their unwavering commitment. I'd also like to thank some other special people in this team. So can Patrick Bellamy, Grace Yang, Lachlan Whitehead, and David Parker please come up to the stage? These 4 comprise the leadership team and are responsible for the direction and vision of Project Lemaire. Simply saying that they've worked hard really cannot possibly convey just how much they've put into this team. Thank you, David, for your unending wisdom and guidance, Lockie for your passion and dedication, Grace for your diligence in everything you do, and Patrick for leading the team with such commitment, integrity, and heart. I hope you all know just how much the team looks up to you. You've done ARES proud, and I hope you can carry that knowledge with you wherever you go. So can we please give them another round of applause? And as a token of our gratitude, we have some gifts for you that I'll give them.
To move my speech over, so I'm just... Alright, well that brings us to the end of tonight's showcase. So thank you all very much for being here, for your time, for your support, and your belief in what we're building. It means the world to our team to have so many friends, family members, faculty, sponsors, and alumni in the room with us tonight. I'd like to again thank our incredible faculty advisors, sponsors, and alumni. Without you, none of this would be possible. And to the ARES team, thank you for the hours, the effort, the passion, the resilience, and the camaraderie. I couldn't be prouder of everything we've built together. Now, before you all go, I encourage you to head out to the foyer, where we've got stalls set up by each of the sub-teams. It's a great chance to chat with the engineers behind the work you saw tonight, ask questions, and dive deeper into the projects they've poured themselves into. And of course, don't forget to grab some food and drinks while you're there. Thank you again for being a part of this journey with us, and we hope you've enjoyed this evening, and can't wait to show you what's next. Thank you.